Hello everyone. In this video, we are going to talk about loop optimization. So the first thing about loop optimization is that the code inside a loop is going to be executed multiple times. So it is a very good candidate for optimization. But before we can go into loop optimization, we have to first detect that there is a loop in your code. So the first thing that we have to do is your loop detection. So a loop, how will we detect that it is there in your code? So usually a loop is a cycle, and using the flow graph that we had constructed earlier, we'll see that if there is a cycle that satisfies two properties, then it is a loop. Okay, so what are the two properties? The first property says that it should have a single entry node or a header. There should be one entry point. Okay, and that the second condition is that it should be strongly connected. That means from one point, that is one node of the graph, there should be a path to go to every other node in that particular graph. So it must be strongly connected. There should be a path from one node to every other node. Okay, so while staying within the loop, okay, that is within the cycle. So these are the two conditions to detect the loop. Now, there are several loop detection algorithms which are available. So these can be used to detect that there is a loop. Now, the next step after this is now we have to improve the working, or we have to optimize this loop. So one of the way in which we can perform optimization of the loop is called code motion. So in code motion, what we do is, because there are certain number of statements or instructions inside the body of the loop, if we remove some of the statements from inside the loop and take it outside the body of the loop, okay, then the time taken, the running time of the program will decrease, since the number of instructions to be executed inside the loop is reduced. So suppose you have a loop which has got, say, let's say 10 instructions inside the loop, and this loop is executed 5 times. So total, you have 50 number of instructions which are executed. Now, out of these 10 instructions, suppose you take out 2 instruction outside the loop, okay, and so you're left with 8 remaining. So you get total number of instructions executed would be 48. So 2 here and 8, 5 is 40. Oh, sorry, 42. So this is 42. So instead of 50, you get 42. So this is your code motion. So based on the running time, that is based on the number of instructions inside the loop, okay, your running time can be improved. Okay. Now, this is based on the assumption that the loop is executed at least once. Okay. So now you have to keep this in mind, that when you take a computation out of the loop, okay, it must not change the semantics of the program. Okay. So in code motion, what we do, we take a computation that yields the same result independent of the number of times the loop executes. So we call it the loop invariant. So these 2 statements that I have taken out will have to be loop invariants. That means they will have the same result irrespective of how many times the loop has executed. So this is your code motion. So in this example, you can see in this code, let me first go to the basic block which has this. Okay, so this was our basic block where we had this. So you can see, you can note here that this instruction, okay, and this instruction, there is a loop here. Okay, this is a loop. This is executed multiple times. But these 2 instructions, this one and this one, these are loop invariants. As the address of A and address of B is constant, and from there you are subtracting 4. Okay, so this T2 and T4 values will remain the same no matter how many times you execute the loop. Okay. But here again, there is a thing that it should be that this loop will execute at least once. Okay. If it does not execute even once, then we cannot say that this is loop invariant. So it must execute at least once. So what we can do with these loop invariant expressions is that we can take them out of this basic block, and we can and of this basic block as well as outside the loop, and we can have we can construct another basic block where we can put these two instructions, and we can put it in before the loop starts. So you can see here this one here. So we have taken out these two instructions, and we have kept it in a new block out here. So we have created a new basic block B3. So this is your code motion. Next, another way of improving your loops is by detecting something known as induction variable. So these induction variables are variables that you use in a loops, which where the way in which this values changes is of something of this format. You see, I is I plus minus C. C here is going to be a constant. So every time I is either incremented or decremented by a constant value. Okay. So the value of C will not change within the loop. So this is known as a basic. In that case, I here, the variable I is known as a basic induction variable. Okay. So X is an induction variable of a loop if every time the variable changes value, it is incremented or decremented by a constant. So loop indexing variables, you have a for loop for I going from 1 to n. Okay. Every time I is incremented by say 1, or it is incremented by some constant value. Then you have expressions of this type, which is dependent on I, and C and D are what? Loop invariants. That means their value do not change during the execution of the loop. So these are also induction variables. So there are two types of induction variables. The first is your basic induction variables, the one which I have already told you about, loop index variables. Okay, so in this loop, it is being controlled by I. This loop is being controlled by I. Okay, I is the here you can see I is I plus 1. I is equal to I plus 1. This I is a basic induction variable. Then you have the second type, which is your dependent induction variable. So in the dependent induction variable, these are basically where you have something like something where the value does not change. So here, in this case, you see T1, the value of T1 is 4 into I. Okay, so depending on the value of I, okay, T1 is changing. Okay, so the value of of T1 will change only with respect to I. So it is dependent on a basic induction variable. So similarly here, you can see product equal to product plus T6. Okay, this is also an induction. This is a basic induction variable. Okay, so these are your induction variables. So induction variables also we can improve with the help of your we can improve these loops with the help of these induction variables. Let's see how. So what we have to do is we have to eliminate these induction variables. Okay, so how do we do that? So when we have two or more induction variables, okay, when we have two or more induction variables, then what we do is we remove all the induction variables except one, all but one. We keep only one induction variable. Okay, so in our example, I is a basic induction variable and T1 is an induction variable which is dependent on I. So we have seen here. Okay, so we have seen here Okay, let me just rub this. So here I is an induction variable, and T here is dependent on, T1 is dependent on I. So we have two induction variables. So T1 is an induction variable which is dependent on 1. Now, assuming that I is not needed outside the loop, what we can do is we can eliminate I in the following manner. So we're assuming that I is only used inside the loop. We don't use it outside. That is what normally happens. No, when we have a loop, we have an index variable in our order loop looping counter. We use it only as a counter in the loop. We don't use it later on. So what we can do is we can eliminate I. How do we eliminate I? Look at the first point. We eliminate I by replacing I in blocks B1 and B2 and B3 by T1. So I, we are going to replace it by T1. So if you look at this code, okay, I, we are going to replace it by T1. And also, so here again, this is another place where I is here. Okay, this is another place where I is here. So that means I have to replace these occurrences of I with T1. So how do we do that? So we'll replace I is less than equal to 20 by T1 is less than equal to 76. Okay, why? Because the values of T1 follows an arithmetic progression with a difference of 4. If you see here, it is going like this. 4, from first it is T1 is 4, then it is becoming 8, then 12, and so on. So every time it is increasing by a value 4. So if it has to run 20 times starting from 0, then the last value would be your 76. So since the value of T1 follows an arithmetic progression with a difference of 4, so we will replace this. Next, what we will do, we will replace the statement T1 is equal to I into 4 is by T1 is equal to I T1 plus 4. Okay, again, it's doing the same thing. It is incrementing by 1. Okay, so since T1 does, and here, since T1 doesn't have an initial value, so we'll say T1 will start from 0. So T1 will start from 0. This is the initialization. So it must go outside the block, outside the loop. Okay, so you can see here now, this one already we had done. We have taken out these loop invariance one because of code motion. Then T1 is assigned 1. So T1 is incrementing by 4. Okay, and wherever there was I, we have replaced it by T1. Okay, and I is equal to I plus 1 is changed. And so this loop will continue how long? Till I is less than or equal to 76, because every time it is increasing by 4. So this way we can get rid of our induction variables. Next, another thing that we can do in case of loops is the reduction of strength. So reduction of strength means, now in a given architecture, you may have different operations which can perform basically the same thing. Okay, like multiplication can be performed by a sequence of additions. Okay, but multiplication is more expensive in terms of execution time as compared to addition. So we can say that if I have to decide whether I want a multiplication or an addition, I will choose addition because it will take lesser time. So multiplication is more expensive than addition. Similarly, if you look at the next example, that is replacing L. So you can see here what we have done, we want to find the length of the concatenated strings S1 concatenated S2. Okay, so if I write length of this, okay, that means first I have to do the concatenation, then I will have to find the length of I'll get the length of the concatenated string. But instead of doing the concatenation, what I can do is I can find the length of S1, I can find the length of S2, okay, and then I can simply add these two. So if this is the operation I have, I can replace it by another operation which will perform the same task, but which will be less expensive. Okay, so this is again another way in which we can perform an optimization. So that is all about loop optimization. So we have seen how we can optimize the loop. We can use code motion. Okay, we can use code motion to reduce the number of instructions inside the loop. We can eliminate induction variables. Okay, we will remove all induction variables except for one. Okay, and accordingly we'll modify the code. And then we can also look at reduction in strength, replacing an expensive operation by a cheaper one. So these are some of the ways in which you can optimize a loop. So that is all for this lecture. In the next lecture, we'll talk about directed acyclic graphs.